Okay, some more practice problems here. We have half a mole of table salt sodium chloride. How many grams do we need to weigh out? So we just need to get the molar mass of it, and then multiply moles by the molar mass to get grams. And then in the second one, we have 25 grams of potassium dichromate. We want to know how many grams of that is actually chromium. So for this one, we can turn the grams of potassium dichromate into moles. Use the ratio of 2 chromium in 1 potassium dichromate to get moles of chromium, and then convert that into grams of chromium. So in the first one, we look at the molar mass of sodium chloride, 58.44 grams per mole. We multiply it by the 0.500 moles, and we get 29.2 grams of sodium chloride. On the second one, we divide our 25 grams of potassium dichromate by its molar mass. We multiply by the ratio of 2 chromiums in 1 potassium dichromate, and then multiply by the molar mass, atomic mass of chromium. And we end up with 8.84 grams of chromium. And we should know that we're going to get a smaller number than 25 grams. We're looking for chromium in the 25 grams, so we have to end up with a smaller number. We could do a mass ratio, which is just another way of rewriting this equation here. So the mass ratio is mass of 2 chromiums over the mass of 1 potassium dichromate. We multiply our 25 grams by that ratio, and we get 8.84. It's the same equation, just written slightly differently. Now we can use Avogadro's number as a conversion unit also. Avogadro's number has units of atoms per mole. So that means we can use Avogadro's number to convert between number of atoms or particles. Generic term particles means atoms, molecules, formula units, ions, electrons, whatever is appropriate unit for us. So we can convert between number of atoms and number of moles. So Avogadro's number there is slightly off. It's 6.022 times 10 raised to the power of 23rd. So to get number of moles, we're going to take number of atoms and divide by Avogadro's number. If we have moles and we want number of atoms, we'll get number of atoms by multiplying moles by Avogadro's number. On this one, we're going to be combining two processes together. So we can go from atoms to mass by combining the process of going from atoms to moles, and then using the molar mass to go from moles to mass. So if we have 3.15 times 10 to the 23rd atoms of zinc, how many grams do we have? How much mass do we have? So we're going to start off with the atoms and divide by Avogadro's number. That will give us number of moles of zinc, and then we multiply by the atomic mass of zinc to get grams. So we end up with 0.523 moles of zinc, and we also end up with 34.2 grams of zinc. We can go the other way. So if we have 1.75 grams of calcium, how many atoms do we have? So we're going to start converting our calcium into moles, grams of calcium into moles, by dividing mass by molar mass of calcium. That will give us moles of calcium, and then we multiply by Avogadro's number to get particles. So we have 0.0437 moles of calcium, or 2.63 times 10 to the power 22 atoms of calcium. We can even calculate the mass of a single atom or molecule. So to get a mass of a single atom of copper, we have number of atoms. Number of atoms is 1. So we take our 1 atom, divide it by Avogadro's number to get moles, then we multiply by the molar mass of copper, and we end up with 1.06 times 10 to the minus 22 grams for 1 atom of copper. So a single molecule of methanol, same thing. We take 1 molecule, divide by Avogadro's number to get moles, then we multiply by the molar mass of methanol, and we end up with 5.32 times 10 to the minus 23 grams for a single molecule of methanol.
We are now going to look at how we describe the composition of compounds. Describe what's in a compound. We start off, one of the ways that we start off is with percent composition. So percent composition is the mass percent of each element in a compound. So it'll be a list that includes all the elements in the compound, and then how much is present in terms of mass percent, which means that the mass percent of all the elements needs to add up to 100%, or be real close for rounding errors, depending on significant digits of the mass percent. We can use this addition up to 100% to help us get the mass percent if we have percent of one or two elements. Just the difference will give us the percent of the other element. And there's a couple different ways that we can get mass percent. One of the ways is from the formula of the compound. So from the formula of the compound, we just look up the atomic mass of each element, add them up to get the mass of the whole compound. So we're getting the molar mass of the whole compound. But then for each element, we'll take the mass of how many atoms are present from it, divide it by the whole to get the mass percent of that compound. For methane, CH4, there's 1 carbon, 4 hydrogens. We're going to add those up and get a molar mass of the whole compound is 16.05. But we have 1 carbon, so that's 12.01 for that carbon. The 4 hydrogens, 1 is 4 times the atomic mass of hydrogen, so we got 4.04. So the percent composition for hydrogen is the 4.04 for the 4 hydrogens divided by the total 16.05 times 100% to give us a percent. We get 25.2% hydrogen. For carbon, we just have the 1 carbon divided by the total, and that gives us 74.8% carbon. So if you're doing mass percents, very good thing just to check your math is see if they add up to 100%. And this adds up to 100%. If it adds up to 100.1, 100.2, 99.8, that's within the rounding error.